Mercury-like planets. Mercury-like planets are small, rocky worlds that orbit extremely close to their stars, in regions where heat and radiation dominate everything. From their surfaces, the star would look enormous and blinding, almost filling half the sky. A single rotation can create a brutal cycle where one side of the planet is baked at extreme temperatures, while the other freezes in darkness for long periods. These planets often lack a real atmosphere because intense stellar winds constantly strip away any gases that try to form. Without air or clouds, the surface remains exposed directly to space, meaning meteoroids hit the ground without burning up and leave permanent scars. Over billions of years, this creates a surface covered in overlapping craters, like a record of endless cosmic impacts. Some of these worlds also show gigantic cliff systems caused by planetary cooling and contraction, where the entire planet slowly shrinks and the crust buckles under pressure. Despite being seemingly lifeless, Mercury-like planets are extremely important because they preserve the earliest history of planetary formation and show what happens when a world gets too close to a star.
Earth-like planets. Earth-like planets are some of the most fascinating worlds because they exist in a delicate balance where conditions might allow life to develop. They are rocky planets with stable surfaces and atmospheres capable of supporting weather, clouds, and climate cycles. If you stood on one, you might see blue oceans, green land masses, moving clouds, and changing seasons, depending on the tilt of the planet's axis. But Earth-like does not always mean peaceful. Some of these planets may experience extreme storms that stretch across continents, volcanic eruptions powerful enough to reshape entire regions, or oceans so deep that sunlight never reaches the bottom. The key factor is the habitable zone, where the distance from the star allows liquid water to exist. Too close, and the oceans evaporate into a runaway greenhouse effect. Too far, and everything freezes into an icy desert. Scientists are especially interested in these worlds because even a small chemical signal in their atmospheres, like oxygen or methane, could hint at biological activity. This makes Earth-like planets central in the search for extraterrestrial life and one of the biggest mysteries in modern astronomy.
Super-Earths. Super-Earths are rocky planets, larger and more massive than Earth, but not quite large enough to become gas or ice giants. At first glance, they might seem like upgraded Earths, but in reality, they are often far more extreme. Gravity on these worlds can be so strong that walking becomes exhausting, and mountains are naturally compressed into lower, wider formations. Some super-Earths may be completely covered in global oceans with no land at all, creating deep water worlds where pressure at the bottom becomes unimaginably high. Others might be volcanic superworlds with constant tectonic activity, where entire regions are reshaped by lava flows and earthquakes. Their thick atmospheres can trap heat efficiently, creating dense skies filled with haze, storms, or even strange colored clouds depending on chemical composition. Because they are so massive, many super-Earths remain geologically active for much longer than Earth, which could either stabilize environments for life or turn them into permanently hostile worlds. Interestingly, they are among the most common types of planets in the galaxy, even though our solar system has none.
Mini-Neptunes. Mini-Neptunes are mysterious intermediate planets that sit between rocky worlds and full gas giants. They are typically surrounded by thick hydrogen-helium atmospheres that hide whatever lies beneath the clouds. In many cases, there may not even be a solid surface in the traditional sense. As you descend deeper, pressure increases until gases turn into exotic super-dense fluids or high-pressure forms of water and ice that behave nothing like what we know on Earth.
The upper atmosphere is often turbulent, with massive storms, constant lightning, and high-speed winds that can circle the entire planet. These conditions make Mini-Neptunes visually dramatic but extremely alien. Some of them may slowly lose their atmospheres over billions of years, especially if they orbit close to their stars, eventually transforming into rocky super-Earths. Their sheer abundance in the galaxy makes them one of the most important discoveries in exoplanet science, challenging earlier assumptions about how planets form and evolve.
Gas giants. Gas giants are enormous planets made primarily of hydrogen and helium, often so large that hundreds of Earths could fit inside them. They have no true solid surface, meaning there is no ground to stand on, only increasingly dense layers of gas that slowly transition into exotic fluids under extreme pressure. As you descend deeper, the atmosphere becomes thicker, hotter, and more crushing, eventually turning hydrogen into a strange metallic state that can conduct electricity. These internal layers are what create some of the most powerful magnetic fields in the solar system, which in turn generate massive radiation belts and glowing auroras near the poles. Above all this lies a constantly moving atmosphere filled with banded clouds, swirling storms, and gigantic vortexes that can last for centuries. Jupiter's Great Red Spot is a perfect example of how stable yet violent these systems can be. Gas giants also act like gravitational architects of their solar systems, redirecting comets, shaping asteroid belts, and influencing the orbits of inner rocky planets over billions of years. In many ways, they are not just planets. They are systems within systems, shaping the architecture of entire planetary families. Hot Jupiters. Hot Jupiters are gas giants that orbit extremely close to their parent stars, often closer than Mercury is to our Sun. At such extreme distances, their atmospheres are heated to the point where metals can exist as vapor, completely transforming the chemistry of the entire planet. A full orbit can take only a few Earth days, meaning a year on these worlds passes almost instantly. Many hot Jupiters are tidally locked, with one hemisphere permanently facing the star in endless daylight, while the other remains in perpetual night. This creates one of the most extreme climate contrasts known in astronomy, driving supersonic winds that can reach thousands of kilometers per hour as heat tries to circulate around the planet. The atmosphere itself can swell outward from the intense heat, sometimes escaping into space and forming long trailing tails of gas that stretch behind the planet like a comet. When hot Jupiters were first discovered, they completely shattered existing theories of planetary formation, forcing scientists to accept that giant planets can migrate inward after forming far from their stars. These worlds are now seen as evidence that solar systems are not static, but dynamic and constantly evolving. Ice giants. Ice giants like Uranus and Neptune are large, distant planets composed mainly of water, ammonia, and methane mixed with hydrogen and helium. Their calm blue appearance hides incredibly dynamic and violent interiors. Winds on these planets can reach supersonic speeds, creating some of the fastest atmospheric currents in the solar system. Their blue coloration comes from methane absorbing red light and reflecting blue wavelengths, giving them a cold, distant appearance, even though their interiors are anything but simple. Deep inside, pressure becomes so extreme that matter behaves in unusual ways, potentially forming super-dense phases of water and ammonia, or even crystallized structures like diamond rain. Unlike gas giants, ice giants contain a higher proportion of heavier elements, giving them layered internal structures that are still not fully understood. Their great distance from the sun means they receive very little sunlight, yet internally they remain active, mysterious, and chemically complex worlds that continue to challenge our understanding of planetary formation.
Ocean worlds. Ocean worlds are planets or moons that are almost entirely covered in water,
sometimes forming global oceans that stretch across the entire surface without any land in sight. These oceans can be hundreds of kilometers deep, far beyond anything found on Earth, and under such pressure, water begins to behave in strange, high-density phases. In many cases, a layer of high-pressure ice may form beneath the liquid ocean, separating it from a rocky core deep below. Despite their watery appearance, these worlds are not necessarily calm. Massive storms, strong tidal forces, and intense internal heating can create turbulent and dynamic environments. Some ocean worlds within our solar system, such as Europa and Enceladus, may hide liquid oceans beneath thick layers of ice, making them some of the most promising places to search for microbial life. In distant star systems, entire planets may be deep global oceans without any continents, creating alien environments where the horizon is nothing but endless water and sky blending together.
Desert planets. Desert planets are dry, rocky worlds where water is extremely rare or completely absent from the surface. Their landscapes are dominated by endless sand dunes, eroded rock formations, and vast barren plains shaped by wind over millions or even billions of years. Because there is so little moisture in the atmosphere, temperatures can change dramatically between scorching daytime heat and freezing nighttime cold, creating one of the most unstable climates possible for a planet. Some desert worlds experience planet-wide dust storms that can last for months, completely blocking sunlight and reshaping entire regions. Others may be ancient planets that once had rivers and oceans, but gradually lost their water as their atmospheres thinned or their stars grew hotter. Even so, some desert planets located within habitable zones might still hide underground reservoirs of water, meaning that life, if it exists, could survive beneath the surface, protected from the harsh conditions above.
Lava planets. Lava planets are extreme worlds that orbit so close to their stars that their surfaces are partially or completely melted into oceans of lava. On the day side, entire landscapes glow with molten rock, constantly reshaped by volcanic activity and tidal stresses caused by the star's gravity. Temperatures are so high that solid rock can melt, vaporize, and then condense again in the atmosphere, sometimes falling back as mineral rain that instantly solidifies upon contact with the surface. These planets often experience continuous volcanic eruptions, with crusts that are constantly breaking, reforming, and being recycled by intense heat. If the planet is tidally locked, the night side may still be extremely hot due to atmospheric heat circulation, creating a world that never truly cools down. Lava planets are among the most visually dramatic environments in the universe, showing what happens when a planet exists in a near constant state of geological destruction and rebirth.
Rogue planets. Rogue planets are worlds that drift through interstellar space without orbiting any star. They are often ejected from their original solar systems after violent gravitational interactions with giant planets or passing stars. Without a star, these planets exist in near total darkness, receiving no sunlight and experiencing extremely low surface temperatures. Their surfaces may be frozen and inactive, but deep inside, residual heat from formation or radioactive decay can still persist for billions of years. This internal warmth may even allow subsurface oceans to remain liquid beneath thick ice layers, creating hidden environments completely cut off from the universe above. If life exists on rogue planets, it would have to survive without any sunlight, relying entirely on geothermal energy sources. These worlds are truly isolated wanderers, silently traveling through the galaxy with no destination, no orbit, and no parent star to anchor them.
Pulsar planets. Pulsar planets orbit pulsars, which are rapidly spinning neutron stars formed after massive stars explode in supernova events.
These remnants are incredibly dense and emit powerful beams of radiation that sweep across space like cosmic lighthouses. Any planet in close proximity would be exposed to extreme radiation levels and intense magnetic fields that would make ordinary planetary environments impossible. Despite these conditions, pulsar planets have been discovered, meaning that some worlds either survived the violent supernova explosion or formed afterward from leftover debris in orbit. Their existence is one of the most surprising discoveries in astronomy because it challenges the assumption that supernova completely destroy surrounding planetary systems. Instead, these environments show that even after one of the most destructive events in the universe, stable planetary systems can still emerge, proving that planet formation can happen in far more extreme conditions than previously imagined.
Thank you for watching. If you enjoyed this video, please support our channel. It helps us create even more interesting space content. You can support the channel via the link in the description or by using this QR code.